So, final talk for today. I think it was a pretty interesting day so far. But most likely the most interesting presentation of today is still to come. As I told you during my presentation, what Dirk basically will do is turn you upside down and start shaking a lot in terms of the knowledge that you gained over the past 1 day and 3/4 of a day, something like this. But I think that's exactly what we are here for, right? So try to challenge you, try to learn you about the most recent stuff. So Dirk, I leave the floor to you to talk about your multidimensional process mining.
Yeah, thank you very much, Jochen. Welcome to this final session in the afternoon. I was scheduled for actually tomorrow. Now you get a big punch towards the end of the day. I put out a couple of handouts. I'm not sure whether there's enough for everybody. Maybe the printer didn't print enough. Maybe you can kind of share. It's not too important if you have them, but it may be handy because I'm going to ask you a couple of questions in between. We're going to solve a couple of exercises together. So try to pass them around that everybody can at least glimpse at the neighbor's side. So what I will talk about is process mining in multiple behavioral dimensions. Now we're going to take this slow. The first thing I would like to look at is a real process. A real world process, and you know, when we do process mining, our aim is to study these real world processes, which is a fuzzy concept in reality. And we have systems that are kind of supporting on controlling these processes, and we use them to record event data, right? The event logs that you've got to know yesterday, and you've learned algorithms to analyze these event logs. Discovery, conformance checking, right? It goes both ways. And these models are meant to describe the processes in reality. If they're good enough, then we also shall prescribe how these processes are supposed to run, either kind of in a fuzzy way or maybe even as implementation models to the systems. Well, this is the world that you've been looking at over the last 2 days. There's actually a picture by Will van der Aalst that I'm adopting here. So let's look at one real world process. We're a retailer who's taking in 2 orders. They come from the same customer shortly after each other, so it's a bit constructed, but it's going to illustrate a couple of things. The first order, the customer orders 2 products X and 1 product Y. And then half a day later, you realize, you know what, I actually need 1 more X and 1 more Y. So 2 orders. Now, the retailer will not order for each order from the suppliers the X's, the items X, right? They will bundle these orders, right? So 3 items X and one item Y. So the supplier, kind of the retailer made some mistake here, just ordering 1 item Y. Now, you also create invoices, 1 for the first order, 1 for the second order. At some point, the supplier order A arrives, it's received, the items are unpacked, and now uniquely identified, X1, X2, X3. We also realize the mistake, update the supplier order. Now for 2 items Y, we update the invoice, and at some point also receive the items Y1 and Y2. To ship the order, we have to have 2 X, 1 Y. So we put them together, and then they're always shipped at 3 o'clock because that's when the logistics provider is gonna pick up the shipments that are ready at the retailer. The retailer has a policy in place that if a customer has 2 outstanding orders, invoices, at least one has to be paid before the other order is going to be shipped. So we first have to receive the payment to clear both invoices, and then the last order is shipped. Okay, that's a process. I think everybody can relate to it in some way. In the real world, well, there's more to it, right? This process doesn't happen in a vacuum. It's being executed by people working on these orders, and the retailer may also have an automated warehouse to manage these things. A typical question that would come, are my key performance indicators met? For example, the retailer may promise that when a customer places an order, within 6 days, it's going to be shipped. Now, we're going to see that this is not true in a moment. So, The first thing that I hope you get from this simple example is the real world is not just one process. It's a complex thing. We have processes, we have actors, we have documents like orders, supplier orders, invoices. We have items that arrive. There's an entire organization behind it. Maybe there's even machines. So reality is complex. Now, how does the event data look like that comes out of such a real-world process with this complexity? Here is the event data that comes with this example. So we have created 2 orders, right? Each order creation creates 1 record in our event table. Order 1, order 2, I get identifiers, there's some details for the order. Then when the supplier orders are placed, I get other events for the supplier order at A and at B, and also the order details. Well, I'm creating an invoice, another event. At some point, I receive the first supplier order from A. I'm updating the supplier order O2 with supplier order B to have other order details. More things are happening, like updating the second invoice, creating this invoice, unpacking the items that have been received, and so on and so on. I think you get the picture. This is the event data that I get for this example process. So here we can already look in this table whether the KPIs are met. It's not too hard. I look for the first event of an order and the shipment, what's the time difference, and then I see then for both orders, I'm not meeting my KPI. One takes 7 days, one takes 8 days. That's something I can already see in this simple table. So now the big question is, why? What's going wrong? Now, here process mining comes in. That's why we apply process mining. We try to understand what's going wrong in the process, why we're not meeting our desired performance of the process. So, in order to do process mining, you've been told the last 2 days we need an event log. What is this? That's the first question to you. People from Aachen are not allowed to answer. Sorry, say again? I mean, it has events, right? Is it an event log? Right, I have a collection of events, but I don't have a case identifier, right? That's what we're doing when we do process mining. We have one column, one case identifier column that would, of course, here I have one column that has this, but actor, right, the person working on it, that's never the case identifier. It's not how we would study the process execution. So we have a problem. It's just a collection of events. Now this is I would call this an event table. You could find this event data also scattered over multiple different tables in a relational database, right? You can easily kind of distribute this based on the different identifiers you see there. So it's a raw event table without any unique case ID. Well, we can do a bit and identify which of the columns here actually are entities or objects. I have orders, I have supplier orders, I have items, invoices, payments. These are entities. I need domain knowledge to see that. To at least have something that's similar to a case identifier, although it's not. So order details is not an entity type because, well, it doesn't really have identifiers, right? It's kind of description of the items I'm ordering. You could also call this, the moment I've indicated what are my object types or entity types, an object-centric event log. That I think was also explained in the very first lecture of the summer school. Okay, great. Now we know we have an event table and no unique case identifier. What do we do? Let's first go down the route of what everybody tells you. Build an event log with a single case ID, because that's how we do process mining. So we have an event table. We need to pre-process our event data to obtain an event log. How do you do this? On the right-hand side, you see the recipe. The first thing you need to do is you have to identify the entities in the data and the relations between the entities. Then we're going to pick one entity type as case identifier, and then we're going to group things. So what are the entities that are in this data? This is a very simple question. There's no trick here. So order is an entity type. That's important to know. Ooh, very good writing. This is an entity type. The concrete entities are O1 and O2. That's right. I have more entities in there, right? Supplier order A, supplier order B, the different items, 2 invoices, I1, I2, and 1 payment. All right. These are the entities, the concrete entities. You have a question? Yeah, very good question. Everybody has this. A thing. So maybe it's easier for you to think of an object, right? An object, a thing that could be a digital document, a physical object, an entity, like in data modeling, entity relationship modeling, right? So an abstract thing, and we'll later on talk about entities which are not really objects, so that's why I'm using the term entity, but for now, think of object. Yeah? Yeah. For what we're doing here, we don't. It's not needed. It's not needed. You're going to see this. Because we just need to look at what the individual identifiers are, and you're going to see it. We don't really need it. Okay, we have our entities. We also need to identify relations between entities. Who can see one relation between 2 entities in the data? That's weird. I don't have a database. Where are the relations? Yeah. Order 2 and supplier order B. Exactly. Right? Here. I have one record. It's event 7. That links the 2. I'm observing an event that refers to both, so they're somehow related. At least I model that they are related. So I can infer which entities are related to each other by looking at the records when 2 entity identifiers come together. So if I jump a bit forward, on the right-hand side now you see the individual entities and the relations. And the arrows indicate in which event record I find these entities to be related. Okay. Now we pick a case identifier to extract our event log. Which case identifier shall we pick? Which object becomes my case identifier? Start with a payment. Why do you suggest payment? It links everything together, right? So that would be the one thing. Then we would have one single process execution. You can do that. Then you're studying the process from the angle of the payment. Not going to do that now because I didn't prepare the slides for it, and kind of calculating this example through now would take too long. We can take a different perspective, and it's typically one that's taken in practice when you have this kind of data, that you don't start with the entity at the very end of the process, but with the entity where the process starts. That would be the order. So we have 2, right? We have O1 and O2. Let's build the case for order O1. I simply take all entities that are related to order O1. I here have the relation, right? So that means I have to look at invoice 1, payment 1, x1, x2, y1, but also b and a. So these are all the entities that are somehow connected to my order. So they have events that have something to do with the order. And then I just collect, suck in all events that are related to these entities. So, which events belong to order O1? I start with the easy one. It's E1. Here. Give me another event. E18, yeah, of course, right, because it has O1 in here. 27, 28, okay. What else? Yes, please. Excellent question, and I won't answer this question. That would be discussed in the lecture that was supposed to be taking place right now, right? So event data preprocessing. So this will be explained tomorrow. Where do you stop? But it comes down to domain knowledge, right? Of recognizing a bit, look, going all this way around doesn't really make sense. And also a couple of database properties that you don't want to go too far over one-to-many relations that you have here in the data. So this is not exact science. This is modeling, what we're doing here right now, and we have to throw in a bit of domain knowledge and common sense. Very good question. So, for now, you have to stick with me and the entities that I've circled here in red. So. Yeah. Yeah. Right, sounds good, right? So that would, for example, mean E6, right? It is related to A, and it has x1 and x2 and x3. We also have x1 and x2 here with relation to the supplier order A, so we should also have E10 and 11. E3, definitely, right? So place supplier order at A, we need it. E8, should we use E8? Yes, no? Yeah. Yeah. Right. So you're throwing already a bit of more knowledge, knowing that O1 will not get X3, right? So E8 should not be included. Although it's related to A, it's not related to X3. So going to filter that out. So you see this kind of going forth and back that you have to do here. I think you get the idea. Then we switch to the slides that summarize what's here, right? So it's all animated. You can also look this back later. What we get by doing this is this event table, all the events that have been connected in some way to order O1, and I'm creating a copy of these event records into a new table. And then creating a new synthetic case identifier, which I, for convenience, call just case. It's duplicating O1 in some parts, but here it's indicating, look, these entities have been remotely related to O1. I do the same thing for O2. So that would be our event log. Now, who spots problems in this event log? Yes, some events are duplicated because, oops, one back. Because, for example, E3, placing the supply order for A, was reachable from order 1 and from order 2, right? Because both orders get items from these supplier orders A and B. So my data says I have 4 times supplier order, but in practice it only occurred twice. That's already bad. something else wrong that I already showed through the animation. Some of the event IDs are missing. Okay, then that would be a mistake on... Oh, yeah, that is because there will be some more events that are introduced later. They haven't been part of the original event table. So it's not consecutive. Yeah, but good spotting. There's another problem here besides duplicating. This is more important. This is worse than duplication. Who sees it? Yeah? Yeah, but that I can't change because this item X3 is just received in E6, right? So this is just there. It's part of the event. I mean, I could filter this out, but then I would be changing the attributes, right? We're now operating on a level of entire events, not on the properties. Payments. Well, it's also duplicated, right? So there's multiple events that are duplicated. Yeah. That is because here X3 is received, which is packed here into the shipment. So I decided to have it because I want to see that item X3 was received, and X1 and X2 are just properties of this. The actual thing that's really difficult to spot is this one says, I've updated the supplier order after receiving the supplier order. But that actually never happened. These are two different supplier orders, A and B. But if you push this into a process discovery algorithm, it will say that you did that. Well, this one not, but directly follows graph, for example, will show that, right? So this one says, this is false behavioral information. I'm never updating the supplier order after receiving it. These are two different entities. So if we give such an event log that's full with this false behavioral information, we get false process models. I see here a loop around placing the supplier order. Right? I have two cases where I've created an order, but then I have this loop around here that says multiple placement of supplier orders, which is wrong. I didn't really do that. I didn't place 4 supply orders. I placed 2. I see false behavioral dependencies and also false performance information. This one says there have been 2.2 days between whatever happened first and receiving the supplier order, but the actual waiting time in the data is 3 days and 5 days. Just because the behavioral information is messed up. I've squeezed things together that don't belong there. So, what did we do wrong? I mean, we did everything you've been told. Yeah, you have a question. Yeah. Yeah. So I think you will still run into issues with the items and with the payments. So I would then, at some point, if I want to avoid all these false behavioral dependencies, I would have to multiply out everything. Well, then I don't have any more meaningful behavior in there, right? If I kind of make the case identifier the combination of all the identifiers I see there. Yeah. It's going to be hard. So yes, you can try, and this is what people do, but I'm here to tell you, you don't have to. Yeet, it's good. So what should we do instead? Now Aachen can answer. What should we do instead? work with object identifiers themselves. Don't have a single identifier in the first place. Don't even try. Work with multiples. The point is, I am unable. You see this, right? I'm unable to separate the behavior into isolated cases and executions. I just can't. But this one assumes cases are executed in isolation. So let's do better. Why? The models that we are creating here that describe or prescribe what's going on are interpreted by all kinds of stakeholders around the process, right? These are people working in the process, managers, customers. And each of them have their own goals, their own actions that they apply to realize these processes. I mean, processes happen because people do work and collaborate. So if I want to help these people become better, I need a model that allows them to communicate about how they're working together. I need an actionable means of communication between actors, stakeholders, managers, maybe even machines. So, what is that actionable means of communication? I say it's graphs, knowledge graphs, by not picking a single case identifier. So what I'm going to do now is I'm going to introduce you event knowledge graphs. We're going to construct one. We're going to analyze them. So how to build one from this table. We'll do process mining on them. Then we're going to go beyond the behavior you've just seen. We're going to analyze actor behavior and complex networks of actor behavior. And I'll close with an outlook. Hoping there's enough time to do all that. So let's build an event knowledge graph. Here's the basic principle. We don't pick a case identifier. Instead, we already did that, right? We identified the entities. And for each event, I'm now going to figure out to which entities does it relate. And then I'm going to order the events per entity. No more, no less. Let's do this together on a simple example, not the full table. That would be crazy. So, I'm going to start. Every event record in this small table becomes a node. I create a node E5. Ooh. Hello. Ah, keyboard. E5. Now you can read it. And I'm going to give this node a label, which is called event. Because later on we'll have also other nodes, which are not event nodes. They're going to be entity nodes and other types, so that we can distinguish different types of nodes. So E5 is an event node, and I can give it all the properties that you see here, right? So it has order is O2, and actor is R3, and a timestamp and an activity. I'll save myself the writing effort. I have another event node, E9, E18, E29, and E30. All right. Created the event nodes. Now, based on the properties that you see here on the table, I create entity nodes. Which entity nodes should I create? Give me one. Yeah, O1, O2, R3, R2, R5. Let's stick with I1, I2, P1. That is enough. So let's start with P1. So I'm drawing a circle. This is now an entity node, right? I give it the label entity, has the ID P1. And I'm recording in the graph which events are correlated to P1 by drawing an edge from E30 and from E29 to P1. Let's do invoice 2. Invoice 2 is down here. An entity node. Ooh. And which events are correlated to I2? E5, E9, and E30. Good. And I1, let's also do this one. That's E18 and E30. So now you already see I have one event, E30, that's correlated to 3 different entities, right? I'm no longer forcing myself to say it's in one specific case. No, it's related to 3 different entities or objects. Now let's order the events per entity. Let's start with I1. How are they ordered? Who's first, who's next? It's not a trick question. It's a very simple one. You just take the events that are correlated to I1, order them by time. Yeah. Exactly. E18, E30. And I can put this into the graph by drawing an edge, a directed edge. The other ones were undirected, but this one is directed. I call this a directly follows edge. And I remember that it's for entity I1. Now I've modeled that from the perspective of I1, E18 is directly followed by E30. Can do the same for I2, which is first E5 to E9, and then E9 to E30. So directly follows I2, I2. And then it's a different color. For the last one from for P1, it's E29 to E30. So, we've just constructed our first event knowledge graph. Yay! It's very simple principles. Create event nodes, entity nodes, correlation edges, order the events correlated to one entity node by time, add the directly follows edges, and you get these paths, these super nice paths, which are local traces from the perspective of each entity. If I do this for my full event data, this is what I get. That's my event knowledge graph. So now I'm not separating the behavior anymore into kind of separate executions. I'm seeing how the different entities relate and interconnect. Who thinks this is complicated to look at? This isn't easy. Let's study it a bit. So, I'm asking you again. What can you see? What do you see in this graph? Anything interesting? Yes. That's a very good start, right? Along each trace, I see the event flow. Along each path of directly follows edges, I see the event flow, right? How one entity kind of passes through time. What else do I see? With a supplier order, what do you mean? Yeah, right. So you're observing the same thing, right? I see these traces, right? These local traces, these paths. For example, for the supplier orders. So you see them also for the orders, for the items. Kind of the layout is a bit annoying, but it's also there, right? I could kind of change the layout. What's special about these two supplier orders? They're very different from the other ones. There's no edges between events of the supplier orders. They're fully concurrent. They're fully independent of each other. The others are somewhere always synchronizing, but these two are not. You now see x1, x2, x3 as dedicated entities, right? And they're kind of separated. But what you also see is, here I have to draw. x1, x2, x3 are created together in this event E6. x1, x2, y1 are merged together in E27. What is this called if multiple things go together in one event? It's a term for it. Batching. Merging or batching? That's batching. Other things? Yes. So we have two events talking about the same activity. We're going to later in a moment also model this, that kind of. We're going to see that they belong to the same activity. Not sure I follow you. I mean, right now I'm just kind of modeling what's in the data, kind of just made choices which entities to have there. We can do more transformations. We're going to see some of these things later. Maybe that's something to discuss later offline. So one thing that is worth noticing is we also don't have just a single start. Right? It means obvious, but so we have start events like E1 and E2, kind of that would have been the start events of the classical sequential cases. But we also have here E6, which is an event in the middle of the supplier order, but it's the start event of X1, X2, X3. Yeah? So events have different roles depending on for which entity you're looking at it. There's more to see. The book chapter describes it all nicely. We go on. So let's analyze where our KPIs are not met. Well, I mean, we could do this on the table before. Now you see it in the graph, right? So we said orders, customer orders, when they're placed, are shipped within 6 days, which is not true. This one takes 7 days. This one takes 8 days. Now the interesting question is, why are they not met? So, yes. Yes. Sorry, say again? I left them out to not make it too complicated. We'll come to them in 20 minutes. At the moment, we didn't construct them, right? You don't see them, but we're going to add them as entities and also their behavior. And then we're going to look at them. Yeah? It was a conscious choice not to include them. So, why are the KPIs not met? Let's analyze this. So let's do process mining. Well, the first thing we need to do, unfortunately, before we can answer the why, is we have to add more, right? So you just observe the actors are not there. There's other behavior that's not in there. Who can see this? Remember the story I told you about the real-life process. What's not modeled in the graph at the moment, because we didn't. Yep, that's right. The actors, right? Gonna save them for later. Something else. Yeah, so I mean, timestamp I have here, and there's a bit that we're also gonna do later about the timing around the shipment, so we'll get to that. Something else is missing. The constraint on the shipment, right? So that I'm not allowed to ship O2 while the invoices are not being paid. Now, in a proper ERP system, you would have a payment block in there, right? And there would be events, so this is a bit constructed. What we didn't model here is the relation between entities, the behavior over relations between entities. We only modeled entities. And the one relation that's going to help us analyze all this is the relation between orders and payments. That's related to the payment block. That's how we can kind of see it back. So this requires domain knowledge. This is not automatic. You have to be really careful when you do this. You have to know what you're doing. But you can identify a relation, like the relation between O1 and P1 and O2 and P1. You can add this as a relation between the entity nodes, right? O2 is related to P1 and O1 is related to P1. Now, a bit your question about relational databases comes in. I can reify the relation into an entity. It's a derived entity, right? It's the pair of the identifiers, O1, P1, O2, P1 of the type order payment. So I have two entities, and I'm correlating all events that are either correlated to 1 or to P1 to this derived entity. So it's E1, E18, E27, E28, and also E29 and E30 for O1, P1. Can do the same for O2, P1. Then I derive, again, the directly follows edges for this derived entity. This is what I get. Some edges I've already seen before, right? These are, for example, here from E1 to E18. They're not interesting. But this one is new. This one says, shipment in O1 happened before receiving the payment in E29. Also, packing shipment, E31, only happened after the invoice was cleared. And also that the payment here was received after updating the supplier order. So, by filtering out the edges that are new, or edges between new edges, I get this graph. So this is how I can infer unseen behavior over relations. It's modeling. Yeah? This is no longer plain data preprocessing. We're doing behavioral modeling here on the level of events. But if we do this, we can analyze, for example, why this shipment was delayed. I start with the event E32. I want to know what happened before E32. Who's at cause that I didn't ship within 6 days? Well, E32 only has one direct predecessor, that's E31, the packing shipment. But who delayed E31? Well, these are those events where I have incoming edges. Who was ready last before E31? E30. So, E7, E8, E21, they all happened before, right? For the packing shipment, I need to have the items there. Well, this one kind of is a bit transitive in the past, related to the order. This one is the last event that occurred before I could do this one. So this one was holding up my pack shipment. The one that finished last before my event is a possible cause for the delay of E31. So if I always look for each event at the one that was the last one to finish before mine, I can build up this chain, this weight chain, right? So this one was 3 hours earlier. If I go back in time, E29, E28, 27, 20, 19, 7, 5, E2. I'm going to analyze this path that goes across all these different entities, look for anything unusual. Well, one of the things that's unusual, and we've already seen that before, right, is updating the supplier order, right? That's one that you actually don't want in there. So, what's wrong with E7? In order to understand that, we have to look at what was before E7. We're going to do that by later looking at the actor behavior. But before I get there, I first want to kind of do a bit of process discovery on these event graphs. So, we've talked about these graphs, modeling the events on the level of events, data modeling the process at the level of events. Sometimes, often, you want to get insights into the data by summarizing it, right? Process discovery. A basic form of process discovery is directly follows graphs. You've seen that. So let's try to apply this here. I want to focus on a small part because doing this on the full graph is too much, right? So I want to look at the orders O1 and O2 and the two supplier orders. They are now the subgraph that I look at, and I want to discover a process model. So, the first thing you've learned when constructing directly follows graphs is to aggregate events to activities, right? All events that have the same activity name are represented in the model by an activity node. Slightly more general term is event class, because it doesn't have just to be the activity name. So in the model that you see in the book chapter, these are event classes. And I can simply, whoops, now I need a different pen. I can simply create a new type of node, which I'll call class of type activity. And I create one for each activity name that I find. For example, create order. And then I just link all events of create order to this activity node. And also do the same for placing the supplier orders, but let's do one other. Create invoice. Yeah, also class node. And maybe also do update supplier order. So create invoice is linked to E18 and E5. Update supplier order is linked to E7. So these are now the activity nodes. How do I get the edges of my directly follows graph to the activity nodes? It's in the picture. I look between any two pairs of class nodes or activity nodes, create order, create invoice, whether I find event nodes that have a directly follows edge. Here. And then just push them up. And add a directly follows edge between them, but remember for which entity type it was. So this was for order. I also have one create invoice to update supplier order. It's also for order. Oops. Let's add one other one. That's the place supplier order. Well, there we are. If I aggregate the directly follows relations between place supplier order and update supplier order, I get also a directly follows edge, but that's for the supplier order entity. So just like the directly follows relations between events are typed by the entities, the directly follows edges between activity nodes are typed by the entity type. And then I can have activity nodes which participate in two different entities, right? Because here I have an event that's synchronizes between two different entities. Alessandro found this out, called multi-entity directly follows graph. It's a standard technique, for example, on object-centric event logs, simple aggregation and event knowledge graphs. So, if we do this, for this example, I get this multi-entity model. Activities, aggregate events, and the edges are specific to the entity type. If I do this for my entire data set that you've seen before, this is the graph I get. Now, that's again quite complicated, but at least everything in there is correct. The really complicated part is this cyan-colored, light blue-colored thing. That is the interaction along the relation, right? That kind of told us how payments influence orders. Can also split this up by creating one activity node per entity type, right? So now instead of merging the clear invoice or the update SO activity nodes together, I have one per entity type and then add the synchronization edges. Maybe that's a bit easier for you to see and recognize. And also translate this into a Petrinet. Then this is called a proclet, where the transitions occurrences synchronize on entities that do a step together. The principle is always the same. You have one model per entity type. By aggregating or kind of discovering a model over the directly follows path of all the entities of that type. And then you either fuse them together, then you get object-centric Petrinets, or you kind of keep them apart with synchronization edges, then you get proclets. So, how far am I in time? It's good, it's good. Let's do a short break from all this technical stuff. What you see here, what I've showed you here, is actually how Carl Adam Petri himself, the inventor of Petrinets, understood Petrinets. So I had the chance to talk to him 15 years ago, 15 years ago. My God, I'm old. And when I asked him, well, how do you explain Petrinets? And he said, when you talk about Petrinets, you don't start talking about places or transitions. You start talking about the tokens. Every token is an object, whatever that is. Order, you as a person, an atom or a molecule in the universe floating through space and time. And when you talk about dynamics of these objects that float through space and time, then most, not all, but mostly you change state when two objects come together. They meet, they synchronize in a joint action. You rarely have spontaneous state changes. So, as long as an atom moves through time and space and doesn't meet anything, it never changes state. But if it meets another atom, they form a joint reaction, something comes out of it. You never have spontaneous state changes. So you can think of the entire universe as objects going forward in time, and whenever they meet, something happens, an event. That's how Petrinets are modeling behavior. It's also how event knowledge graphs are modeling behavior. Every single object has its own path through space and time, and they meet and synchronize. Nice thing is this is not purely theoretical. You can work with it. You can use a graph database system like Neo4j and Cypher queries to construct event knowledge graphs from event tables. To do everything I've just shown you, inferring entities, directly follows path, relations, aggregation to models, and so on. There's a link to tutorials that you can try out. Still working on some of the tutorials, but the basics are there. Everything that I've showed you until now is already online. Okay. Any questions at this point? Yes. Ooh, yeah, very good one. Let's go back. Oh, no. Here. Super tiny. The timestamp here at the bottom. Also in the printout you see it, right? So this is a timestamp, 9th of May, 11:45, 9th of May, 8:45, and this one is 7th of May, and this has 4th of May, and this also has 4th of May, right? So that's how you would see this. It's simply looking at the timestamp. It's just very, very small. Yeah. Ooh. I don't know who was first. I go from left to right. I'm sorry. Yeah. You can. I'm not going to make one up right now. That's gonna go wrong, right? But I mean, any KPI that would matter for the process, as long as you have the attributes in the data to analyze them, well, then you can do this. I'm not saying every KPI needs event knowledge graphs. Also, let's also make this clear, right? So, I mean, some KPIs, just as I've shown you in the beginning, you can just look up on an event table. But if you try to understand, for example, why things are delayed or why you have rework, then you need to look at cause-effect relations or possible cause-effect relations in the data, and that's what the graphs are going to help you. I also know that certain KPIs are better to compute in this graph setting, right? I know the time between the creation of the first order and the shipment of the last associated order, for example, I don't know whether that makes sense, right? And then you kind of go across. But there are examples where simply sticking to one identifier just doesn't do the job, and then you need these graphs, as far as I can say it. Yep. Yeah. So the graphs can be built. What I've done over about 1 million events, 1.5 million events, fairly decently just on a simple laptop. That works fine. Analyzing it, well, this is my current research. So to some extent, you can see what I've just presented to you, like process mining 15 years ago. We knew what event logs are. We had basic analysis algorithms on them. But the whole industrialization that happened in these 15 years until now, that's still to take place. I hope it doesn't take 15 more years to get there. Ulla.
So my question was a little bit in that direction. So a few slides before you just told, oh, it's complicated. Let's talk about the story. And you know, it's only one story. And you've seen probably like the Neo4j graphs with 5,000, 10,000, or what I have like 100,000 cases, 1 million cases. What do you expect the end user? What do you want to show him? Because you were talking about like directly follow graphs is wrong with some KPIs, yeah. But it's still like this there's an intuition behind it. So what's your idea about what kind of visualization, what kind of presentation would you have for your user?
So it will rarely be the full multi-entity directly follows models that I've just, or multi-entity models that I've just showed you. It would be what we call local process models. It's an active line of research where you define views on the data around one particular type of dynamics that you want to see. It's an active line of research. It's difficult to obtain these because if you apply approaches like association rule mining, bottom-up discovery, you get tens of thousands of models even on classical sequential event logs. Mm-hmm. So you have to be really smart. We have to combine domain knowledge here with kind of scoping this up. In the end, I see a combination of discovery and querying, right? So where you say, okay, I need to analyze things between point A and point B. Mm. And then you have two endpoints where you kind of can scope down all the events in between these two endpoints, and then you can narrow it down of what you would like to discover. Yeah. It will always be a world of multiples. I mean, we have multiples here, the models will also be multiples. It's inevitable.
So we had workshops with our users about this one, what they would like to see, and they were like, please filter the first part. I want to generalize. Please show me the details in the middle, and the end would be like generalized again, so it's pretty much what you say. Yeah.
There's more things you can do that I cannot talk about because it's under review for the ICPM conference at the moment.
Okay.
So, let's wait about that. Yeah.
So I have a question that if there is some entity which is replicating itself, like there is, if there is some loop, because the output is directed graph, and if there is it a possibility to have a loop? First question. If it is, then how this graph will handle this?
Yeah. So you can have loops. See a very simple loop down here, right? So where the supplier order is unpacking multiple items one after the other. The point is that here you see a repetition of behavior within a single entity. What you're talking about is where I don't know what that example would be, right? I have one entity K1 that then instantiates another entity of the same type K2 and then K3 and so on. They're separate identifiers, so they become separate entities. The model is going to look ugly, right? So the discovered model, that's clear. One of the things that I would then go for is, instead of aggregating everything here, rather use techniques like sequence diagram, UML sequence diagrams, where you have multiple lifelines and you kind of separately distinguish different entities, especially in these kinds of self-referential behaviors.
So it means that unpack can only replicate itself for 5 times. So we have a counter of self loop. So that's why it will not be infinite.
So, well, no, say again.
Like unpack, and there is a self loop.
Yes.
So there is also a limit, like 5. It will replicate itself 5 times, so that it will not enter to the infinite loop, or counter saves the infinite loop.
Like so this is basically a question about what do loops in process models in general describe, right? I mean, this is not just this one. This is any kind of patrinated model that has a loop that you've seen before. The loop that you see here, in principle, allows for infinite iterations.
Yes.
But we assume some form of fairness, that when you enter a decision point, do I go again through the loop, or do I exit the loop? If I visit this infinitely often, at some point I'm going to take the exit and not go back. And that, by that, say, small trick, we will always have finite behavior that leads us to an end. So we're never studying infinite behavior. The loop theoretically would allow for an infinite, but in practice, somebody at some point runs out of items to unpack here, right? So
yes, sure. Thank you.
Yeah. So that's an assumption that comes with it. Last question. I have more things to show.
Thank you for the talk. So I'm just thinking here, if I compare with the object-centric process mining and object-centric event logs, so in the end, I think it boils down a bit to the storage format that you're using, because the information is kind of the same, right? So the question would be then, what would be the advantage? Because in my view, it's kind of like, if you can use graphs and then you have a query language that's easier to use because of the graphs, then I see an advantage. But I didn't see the queries that you use to compute those KPIs, so I cannot evaluate. And then the first question would be, okay, how does the queries that you use look like? So are they complicated, and do you need a lot of expertise? And how do you estimate the effort to actually, let's say, implement a language that facilitates that, like BigQuery, but for your storage format?
So there were lots of questions in there. I think I can't answer them all. Query languages at the moment, there's Cypher. Interesting research, what this kind of, it's like SQL, but for graphs, right? If you want to do like process analysis, you also don't want to use SQL. You want to use a higher level language with the right primitives. Needs to be developed. KPIs, same thing. Currently working in a couple of industrial case studies to kind of work out what are the KPIs of interest, how to develop them. This is new, right? This is fresh off the press. You can't expect me to have answers to all these questions on an industrial scale, so this is ongoing research. The essential question that you had, how is this different from object-centric process mining? Until now, I've just essentially covered object-centric process mining, and now we're going to go beyond it. So here's a couple of other graphs that kind of are obtained from real-life data. So this is the BPI Challenge 2017 data, distinguishing application documents, different offers in orange that are created different points in time, and also the workflow application, this is the light blue that goes over it. You can discover these multi-entity models compared to, say, classical directly follows graph models, which are have many wrong edges, as you've seen before. Even if you try to use a more sophisticated algorithm like the split miner, the problem remains. It's more natural to think of the different entities and objects. Well, as I said before, object-centric process mining, here you see it working. This is interesting. This is maybe slightly more complicated than what typical object-centric process mining looks at. The BPI Challenge 14 dataset is an ITIL process. So you have hardware components, software components with a very, very long lifetime that kind of serviced over a flexible, knowledge-driven process. And you see here a very complicated network of all these things interacting. I have no idea what a good process model is here, but at least now all the data is properly connected and we can start looking, for example, for patterns. Let's look at where event knowledge graphs go beyond what typical object-centric process mining looks at, actor behavior and queuing. So remember, kind of half an hour ago or so, we stopped here with the delay analysis, seeing, okay, somewhere here this update supplier order was along this chain of delays, and that could have caused or contributed to us not making the KPI of 6 days. Let's add the actor perspective to the graph. You've asked about this before. So actor is an entity type. I have 5 different actors. If I add actor R1, here to be type is actor, as an entity, and then compute the directly follows relation over it, this is the path that I get, right? Actor R1 first does E1, then E2, then E3, then E7. That's what you see in the data. So this is the path that actor R7 follows. If I do this for the other actors, this is what I get. I can identify task executions, larger units of work that one actor has done. R4 first does pack shipment and then ships. 2 subsequent actions on the same object, and then they move over. And guess what? They do the same thing over here as well. So there's a regularity, and there's also a larger unit that goes beyond the transactional events that are recorded in the data. These are all the task executions that I can find here. So this one I've already talked about, right? The same, slightly more complex task executed in different cases or objects. That's sequential batch processing. First one, then the next. Here's also sequential batch processing by R2, receiving the supplier order, unpacking it, first on A, then on B. But in the first one, R2 is interrupted to update the invoice before they go on. As a process manager, I would get nervous when I see this. Other things we see. R1 and R3 do single action task, right? But something is off, right? So R1 creates both orders, then places the supplier order, but R3 places the supplier order for B, and then does creating the invoice. So maybe that was the cause why we had to update the supplier order. Remember that kind of here there was just one Y added. It wasn't the same person who created the orders who also placed the supplier orders. So maybe that is the reason why things went wrong here. can see this from the actor behavior. It's also here kind of how this comes back in the data. Can integrate everything. Now it's going to be amazing. So let's put all the things I've shown you together so far. Looking at a small part of the graph, right? So we had here the supplier orders A and B, and then the part of the behavior of R1, and then R2 kind of going over it. We've identified these subgraphs where one actor does multiple steps for one object, like R2 going over multiple steps for B. Can aggregate the subgraph into a node, a new node, just like how we previously aggregated events with the same activity name into a node. Now I'm aggregating multiple events that have the property, same actor kind of does them subsequently on the same object into a new node, which I call a task instance, because it's an instance of executing a task, and the name of the task is receive supplier order and then repeated execution of unpack. Can do this for all these task instances that I find, and I get this. And just how I before did process discovery by lifting directly follows relations to class nodes, I can now lift directly follows relations to task instances, the directly follows edges along the case, as well as along the actor. This is simpler. This gives me a different view on the data. And this is what the ICPM paper is about, but I'm not going to tell you. You can do much more with it. That's what I'm not going to show you. But one other thing we can do, right? Of course, we can aggregate these task instances because they are just like high-level events that aggregate multiple lower-level events. And I can now aggregate them to task nodes. They're like class nodes for tasks, right? So TI21 and TI6, they're both receive supply order and then followed by unpack. So I can aggregate this, can check for the count. And then I can use this information, right? I'm building up this graph to filter and do other kinds of analysis. For example, I want to, for all tasks that were executed at least twice, which is place supply order and receive supply order unpack star, pick all the events of these frequent tasks, right? So I go up in the graph, lots of colors, but you see all the events which are kind of involved. And then I want to discover the process model of the activities of these frequent tasks. So I now do the aggregation we've seen before for the process discovery, right? Now I get directly follows graphs for the actor behavior. I see one actor kind of, so place supply order is executed twice, and then I have here this loop, this task execution of the receiving the supplier order, then unpacking multiple times, then this iteration of the loop, which is this one that you see here, going there. So I'm integrating lots of things to dive deeper into the data and provide more context to the analysis. Can do one more thing. There's alignments in here. The model says, for the frequent behavior says, after unpack, I do unpack. Or I go back to receive supply order. But in the data, I have this path, unpack, update invoice, unpack. So I have a move on log compared to this edge. Basic forms of alignments. I'm no longer having event knowledge graphs. I'm building a process knowledge graph. Now, if you ask me, how can I apply this in industry? Look, I just figured this out. We need to, there's so much research we can do here. I mean, throw in documents that describe these processes, do natural language processing, I don't know what. The world is open. There's one more thing we can do. Oh, yeah, real-life data, right? So analyzing these actors and super complicated networks and very interesting patterns you can find there. And then, well, it's difficult to squeeze this from the angle of object-centric process mining. We can split hairs about terminology, but somehow the actor now kind of exists across all these different executions. It's not an object in a case anymore. It's something different. There's one thing we didn't discuss yet. I mean, we figured out that this update supplier order kind of was annoying, right, and kind of probably contributed to the delays. But, well, did we really analyze everything? There's one more type of entity we didn't analyze. Who remembers all the different columns? You have the sheet there. Look at the columns on the sheet. Which column did we not analyze yet? Sorry, say again? Invoice, we did all these entities. Look, they're all in here. They're all in there. One column we did not analyze. Also, payment is here. I mean, we didn't discuss them in detail. Order details, that's one interesting one which I won't cover because it's actually state information about the order. I'm just talking about the events, but I'm not really talking about the state information of the order. We still have to put this somehow into the graph. Will be very interesting to do. But there's one more column that we didn't look at. Actor we did. Time is already there. Of course, I mean, wouldn't want to make time an entity. Payment, we're all there. They're all there. They're all there. The columns are there. There's one column that's not there as an entity. It's the activity column. The activity column is not an entity. Are you going to say Dirk is nuts? Activity as an entity. I'm going to show you. It's going to show us something really nice. The reason is, right? The shipment is scheduled to always happen at 3 o'clock. Here, 3 hours before, so this happens before, right? So on 9th of May, 3 o'clock it's shipped, 11:45, the shipment is packed 3 hours before the clear invoice is done. Here, 17 o'clock, so after the 3 o'clock in the afternoon, shipment is packed, and it takes 6 hours between the last event, unpacking event, shipment. So here, kind of the delay was on the clear invoice. There it was taking so much longer. What's going on in here? And that's because we have this warehouse in the background that was also doing things. I didn't show this to you yet. So here's more data from the warehouse. Can integrate this into the graph by deleting all the directly follows edges of the items that I have so far, adding more events, correlating them, adding the new directly follows relation. Then I have a partial graph, or I have a graph, and I extend it with new information. Now, I make the activity an entity. So that's not a class node, it's not now an entity. So receive supplier order is now an entity, and I add the directly follows edge for this one. What is this going to show me? Well, let's do this for all the activities. Who can see something here? What's the space between two activities if you kind of look at the behavior along two activities? Anybody doing operations research? Nobody. It's queues. Let's transform the graph, give it a better layout, and just focus on items and activities. Yes, there it is, the performance spectrum. So I've now, the events are now really small, right? So, but these are the events. These are the directly follows edges for the activities. These are the directly follows edges for the items. I've spaced them out over time. Can you see something now? So batches, definitely, right? We've seen the batches before, but now they're kind of more obvious. That's interesting. Something else, what we can see here? Yeah, that is because, right, the supply orders, they come in relatively late and kind of things are sitting around there. And then for the first one, we're waiting for the supply order B. For the second one, we're waiting for the payment, right? So that's why we have these large amounts of time in between. There's something else, especially when we are looking at this one, right? This one, what we're worried about. It's not making the pack shipment for order 01. It's not making it before the 3 o'clock deadline. Can you see why? So you see here around scanning, right? So I first unpack Y1, but I'm scanning first Y2. This is not FIFO. The one that I've unpacked first is processed at the end. So I see overtaking. And I'm losing time because of this. I'm losing 2 hours here and 50 minutes over here. Well, this is 5 o'clock, this is 3 o'clock. If I would be taking the fastest route through this, I could make it. Now, it's all very nicely constructed, right? But it matters. It matters a lot, right? If you analyze event data from logistics systems, that's exactly what you're looking at. Minute differences between an item making it to the point where things are shipped and the airplane leaving. It's exactly what you're looking at. This is how this looks on real-life data. Whoa. Road traffic fines process. Some of you have seen the data. Batching, straight-through processing, higher priority, FIFO, more batching. You get a completely different idea of how process performance actually takes place. And now you wonder whether remaining time prediction, the way it's being done, is actually done in the right way if you just engineer features based on a case. So, let's wrap it all up. What did we just use? We looked at a process, like this order process. And it's constructed to kind of contain lots of things. It's a bit over-engineered, but it has many elements of real-life processes in there. We used event knowledge graphs to model the behavior over data, objects, and relations. Object-centric process mining. But the nice thing about these graphs is we can analyze edges and the activities that are causing delays, synchronization, batching, all kinds of interesting features. We've analyzed behavior over actors, right? The task patterns, and we've seen inefficient work division. One actor doing things they're not supposed to be doing, actors getting interrupted in their work. And we've looked at behavior of activities, so queues, inefficient prioritization. So if we bring it back, then the single case ID-based process mining that you've studied until so far is studying behavior for one case object, right? One case, and one dynamic, one flow, one sequence of events. That's how you study it. But out there, there's a much larger world of workload, queuing theory, networks of actors and objects, multiple actors that are studied in different disciplines, like organizations research, operations research, multiple entities, social networks, information systems with complex databases that have related objects where the relations are not also fixed, right? They change over time. Relations are created over time. They get added, they get deleted. So if you have all this, but you only study this, then you're actually studying a point mass in a vacuum. It's nice, right? Physics, point mass in a vacuum. Formulas are simple. You get a lot of things done. But in engineering, this doesn't get you anywhere. You don't actually solve problems. So you have to reach out. You have to include multiple objects and also analyze multiple flows. And I've basically shown you the tools to do this. Event knowledge graphs to handle multiple objects. The performance spectrum, behavior over activities to analyze multiple flows. And actor behavior that actually looks at multiple objects and multiple flows together and kind of how actors navigate through it. Gets to a different way of thinking about processes. Makes your brain hurt at times, I'm honest. But it's worth it. That's all I had to say. Thank you. Still got time for questions. Yeah.
Thank you. The relationship between entities that we found, it seems, maybe I understood wrong, but it seems that it really relies on the initial relationship that we were looking at. And it seems a manual process, or I wonder, is there a systematic way to do it? Is there methods that you suggest or you developed?
Yeah.
Thank you.
So very good question, right? So what I've showed you here is kind of we relied on two entity identifiers showing up in the same event record to kind of infer the relations. I mean, if you have no other information, it's a good starting point. Well, luckily, most processes are supported by proper relational databases. So, well, you have a relational database with primary foreign keys, so you can leverage on this. That's where I would start. If the schema, the data model, is not documented, there's different ways for recovering, right? So the schema recovery techniques to identify entities, relations. There's ontology-based data access techniques that Marco is also, for example, researching to kind of, because these database schemas often are highly engineered. Think of SAP data models, right? So they have nothing to do with the conceptual model. So you have to do a transformation of the database schema into the conceptual model. So these things are there that help you to kind of translate and identify what are entities, what are relations. There's some references in the textbook to kind of help you do this. Some things are implemented, some things are not. Yes, please.
Okay. So my question is, if we have an organization that already stores their data in a graph database, then I guess everything is fine. But if this is not the case, would the suggestion be that we transfer all the data they have, and then whenever we need to analyze something, we use the graph database? Or is it in specific situations when I just want parts of the data to get it there and then analyze it?
Yeah, very good question. I think by what we know now, and also the performance of graph databases at this moment, I would go for analysis-specific construction of event graphs. You've seen we've made lots of choices which entities to include, which relations to include. If you kind of try to do this, kind of preparing for all kinds of analysis use cases, you're kind of just going to blow up your database and not see anything. So for the moment, especially anybody who's kind of trying to explore this, do this for specific analysis use case. There's lots of still creative modeling taking place. In the long run, I think, that's my personal belief, we're going to move to graph-based storage also for event data in information systems. So relational stores will disappear. That's just a matter of time, of sufficient performance of these graph database systems, and us knowing how to industrialize these concepts in a way that when you start building these graphs, yeah, you do that for the right kinds of analysis, for the different analysis questions that are there. What I imagine is kind of, it's a layered architecture where kind of at the bottom you have all the events that are there, the base entities and relations, and then you add on-demand entities, relations, behaviors based on the analysis question that there is, kind of querying. You ask a query, kind of generates the additional data, caches what needs to be there or throws it away based on the analysis workload.
And the new paper now will tell us more when we want to use the ICPM paper.
Yeah, so the ICPM paper is what we put down there is showing a completely interesting way of analyzing behavior in event graphs that has nothing to do with analyzing objects, getting insights into organizations. There's one more question.
Thank you very much for putting so much perspectives into one model. I really directly fell in love with it, I have to say. One question about analyzing such a huge thing, which looks, first of all, like a spaghetti process. Would it maybe help to have a different kind of visualization? Maybe think about like a 3D kind of visualization where you can like pack a lot of different things into another dimension where you do not have these overlaps of all the edges and the arcs, and if there's a possibility for cooperation on such thing.
Very likely, yes. I still want to walk into such an event graph, right, and kind of move the nodes around. And I think at some point we will need such techniques, especially if you are dealing with a very complicated case, and then these 2D visualizations are limited. I have no experience with doing this, and I think what my fantasy produces is maybe not realizable, to be honest. But I think it's definitely an area worth exploring.
Because we are like visualizing this, and I have the feeling it directly follows graph in 3D. It doesn't give you any further information, but what you're like working on with event knowledge graphs, has the potential to do really a huge impact in 3D.
Objects, the actors, the cues, then suddenly you kind of, I agree.
Let's maybe get into chat afterwards, if that's fine with you.
Definitely.
Thank you.
Okay, so thank you for your presentation. Very interesting. So I have a question, like more on the implementation side of the graph database. So is there? I mean, I have like the Neo4j whatever database on the one hand side. I have this like very formal concept of actually how we can specify event graphs. I have entities, etc., entity types on the other hand side. So is there something between that gives me, like, given a database, I have a proper description what this database actually contains? Because in the worst case, I will tell you, here's my event, here's my my graph. I just connect randomly things that I'm not supposed to connect, but it's quite difficult to check because the graph allows me to do that. And actually, I have somehow fearing that someone gives me a database and I spend like hours and hours, similar as if someone gives me like, here's my snapshot of my Windows Access database, here are the tables, and no idea how things are linked, and you explore these things for hours. Is there some description in between or available that actually explains me what the graph actually contains? And
so you're asking for a data schema,
yeah, to some extent, yes.
Right? So Neo4j has a simple feature that kind of can summarize how the different labels and kind of relations are connected. The way how I use it at the moment, because the entity types are properties that wouldn't be visible, so you would just have to specify it. I think it's not too hard to also specify this data schema as part of the database, and it can also do integrity checks against it. It's just a matter of doing it. The problem is there's at the moment no standard language for specifying data schemas in graph databases. It's ongoing research, so this is a tough thing, but it's just a matter of, I don't know, 1 to 3 years until it's there. Thank you. You made it.